Okay, we've started the recording, and we started a little late today, so
Bianca had a question.
great. Let me. Can you explain again why the second one is x greater than or equal to 0? Okay. Okay. So let's go. So we're dividing the x-axis up into everything over on this side, and that's x is less than or equal to 0. And then everything from there to the right, and that's when x is greater than 0. um, Now, it's kind of interesting. Some folks could look at this, and when they first teach this in, let's say, college algebra class, we teach piecewise functions. I always get a number of students who want to characterize one half of the graph by the y-coordinates. They're going to say, all right, when the y is less than 3, then we're over here on the left, they say. But actually, you're over here on the right as well. When you're taking the y's less than 3, you're not getting a unique portion of the graph. This graph is not what we call a one-to-one function. Horizontal lines cross both portions. This over here on the left and this over here on the right. And so the only way to get a unique portion of the graph is to specify intervals along the x-axis. Because it's a function, if I say x less than 0, I'm going to get a unique portion of the graph. Passes the vertical line test, so any vertical line will only strike the graph at least once. And then to the right of it, when x is greater than 0, I'm having this portion of the graph. Bianca, does that clarify your question? Does that answer your question? And I looked at the feedback quickly,
So,
and
Mr. Shankin, I can't see anything again.
you can't see anything?
No, I see that you're live, but I don't see anything as I'm watching stream, but it's a black screen and it just says player popped out.
So that means that your window popped out of the screen.
So I think what you do is you exit the live screen share and then reinitiate it. Click on my name again under voice channel and join the stream.
Okay, let's see if that works.
Did that work?
I think so. Are you showing problem 2 right now?
Yes, I am.
Yes, thank you.
Okay. And every now and then that happens that people kind of lose the stream, and if you just click out and get back in, that should reinitiate it. All right. All right, let's go to number 3 now. Let me give everybody a minute to work on that. All right, does anybody still need more time on that? All right, let's look at it then. So when I shift something up, that's the easier one. All we do is put a plus 3 at the end of it. When I shift something to the right, then I replace the x with either x plus 2 or x minus 2. Now this right here, we call this a vertical shift. And vertical shift are the same direction as the sign. So plus sign means you go up in the vertical direction. But horizontal shifts is when you replace the x with something else, it goes opposite direction of the sign. Now my first instinct would be to think, oh, I'm shifting it to the right 2, and I go x plus 2. But if I did that, I would be wrong. That is actually going to shift me to the left 2 units, because horizontal shifts go in the opposite direction of the sign. So the correct answer here is going to be minus. Alright. And so that's the correct answer. Let's go back to the main screen. Give me a little feedback. Rusty with this. I'm not sure I'm understanding. I'm totally okay with this. There's lots of variation in between. Tell me what's going on. Okay, and it might depend a lot on how much your pre-calculus instructor emphasized these transformations, how much time they took for this. Okay. All right. This next one, difference quotient for that function. And this is one that was in the homework. Similar to one that was in the homework. Excuse me. All right, so on this one, I'm going to give you one more minute, and you probably are not going to finish fully, but you'll be able to check what you've done so far on it. Alright, so I'm going to start on this, and I'm going to figure out what this portion is right here first. And for this particular function, what this really means is f of anything is 2 times that thing squared minus 3 times that thing plus 1. So I am going to take 2 times and fill in all those blanks with x plus h. And then when I square this out, I have to FOIL it out. When I FOIL that out, I'm going to get x squared plus 2hx plus h squared Now even these little things like the 2hx, I'm careful to always put those in alphabetical order because I might have like terms that I don't realize that they're like terms because I didn't put them in alphabetical order, so I always get in that habit. Oops. Alright, now there's no like terms here, but this is what's going to replace what I circled right up there. So my difference quotient is now going to be that whole thing
Wouldn't that h squared be a 2h squared?
Thank you very much. Minus, oh no, this
That
is,
should be the original equation.
Hello?
yes,
Hello?
my eraser,
You can try Control Z, that'll undo stuff.
Control C
Yeah.
Hello?
for like erasing.
No, Control Z like
Hey, no problem.
xylophone.
Control Z does undo stuff. So you don't have to keep erasing and then switching back to pencil.
Neat. Thank you. Alright, so minus, and then what redoes? Is there a something for
Control Y.
Control Y? So where was I at here? Minus 3x
That's 3h plus 1.
plus 1 minus, now the f of x all of this over the h. Okay, and I'm just going to go into red ink for a moment, and I'm going to realize that this and this will cancel each other out. Go to blue ink. These.
You know, I think that in the there's originally you had a 2h squared, and that didn't carry down. It just
Oh,
the
thank you.
2 was lost there.
Thank you very much. Okay, and then I'll just go to green, and we'll see that this one cancel out. So then let's scroll down a little bit. Oops. Alright, I'm still figuring this stuff out. Come on. There's a little delay here. So then this is equal to, now everything that's left over has an h in it. I'm going to factor out that h. And I'm going to be left with 4x plus 2h minus 3. And that's it. All over h. And then the h's cancel out, and I'm left with 4x plus 2h minus 3. And that's my final difference quotient. All right, now let's go back. Give me some feedback on this. Totally lost? Got it? Anywhere in between? Need a little more practice? Any kind of stuff. Okay. I'm looking pretty good on this so far. Okay. Good feedback. And that's something we'll get into later. So that's the part we're done with the practice quiz. And there was a question at the end of class last time about how the tests are going to run. And also I want to go over, so let's get into Canvas. So the syllabus, at the bottom of the syllabus, if we go all the way down there, we also see the schedule, but it's not so good because it doesn't have all the grid lines. So you can also see the schedule in, let me make a whole new one here. In the modules. So you'll notice that on test exam days that we're not covering new material. Exam 1 and exam 2. On the exam days, all we'll be doing is an exam. I won't have you don't have to have a lockdown browser. You're on your honor to do the exam just like we would do it if we were in a live class. And we'll have the entire time, 11:30 is when the exam time will start, 1:45, so you'll have 2 hours and 15 minutes to do the exam and then to upload it. So the exam will be set as a module to open and close at the beginning and end of that window of time. And what you'll be allowed, if there's any formulas that I allow on that, I'll be real clear about that, but generally speaking, unless I've specified it, you cannot use a textbook, you cannot use any other forms. And you can use a non-graphing calculator on the exams. Any other questions about how exams are going to work or any of the other stuff?
Could we go over some questions for the homework?
You bet. Let me finish with some of the things for the class in general, and then I'll go right to homework questions.
So the exam will be written on paper, and we'll just take pictures and upload like we do the homework?
Correct. I mean, I could put it in two different formats, in Microsoft Word and in a PDF file. So, if you wanted to type in some of your answers, you could do that too. But generally speaking, most people write it all out and then take pictures and then upload that.
Is it true that we get more points if we write it out?
Well, I want to see all the work, definitely. So I grade the work as well as answers. So I don't give credit if you just give me answers without the work shown. So that part is true, that you gotta show me the steps. And the general rule of thumb, and it's the same with homework as well as with exams, is if you're skipping steps that I could not have skipped, then I don't give you credit for it. I need to see how you're getting to your answers. Okay. Otherwise, I don't care whether you're typing it in or just writing it in. It will be handy if you get a scanning software, a scanning app on your phone. They take much better images that you can upload. And you can upload it then as one file. And so multiple pages, it's way easier for you all, and there's lots of free scanner apps. You might talk with some of your other classmates about which ones they tend to use. Let's run through some of the things for the exams. On the syllabus, it says, all right, for the two of you that weren't here yesterday, on the homework, there's what's called a spot check, which means you're going to get homework today, which is section 1.2, and before you come to class tomorrow at 11:30, have at least 75% of that done and uploaded, and that counts as a spot check. That doesn't have to be the final version of the homework, though. You have until Thursday, usually at the end of the week, you're turning in, make sure the final version of the homework is in. But you want to be up to date each day so you can ask good questions about the homework. The exams, if you miss an exam, you need to contact me beforehand. If you just totally miss an exam and then say later, I was out of town or something, it's going to cost you 30 points. But I'm extremely flexible if you let me know beforehand, and if something's come up or something like this, or you had a sick child that day and you couldn't do it, I'll take care of you. But if you just are not putting it as a priority, it's going to cost you 30 points. Final, you must take it in order to pass the class. Tardiness, we'll start promptly at 11:30. Please do not be late. Late work, it's a really big penalty on late work. One late written assignment can be turned in with no penalty. Further lates, you get only 50% credit on those. And the reason why I'm so adamant with this is it's really hard to succeed in a tough math class when you're constantly behind. And so I put an incentive system in there that it's you really got to stay on top of it, and it'll pay huge dividends for you. And again, I talked about this yesterday. If you have a situation though where you need additional flexibility, you have kids or a job or something like this, or you just let me know. But you have to let me know at the beginning of the semester, or as soon as your job situation changes or something like this, and then I'll give you all the flexibility you need if that's the case. Absences, anytime you're absent, I always want to be informed. So send me an email, tell me what was happening, and always return the next time caught up, if at all possible. Don't show up and say, hey, I missed the last class, and I don't understand what's going on. You'll be totally confused the next day as well. If at all possible, get the assistance you need so you get the material from the previous day understood. Tutoring Center, it's on BrainFuse in Canvas. On the navigation screen on the left, you see towards the bottom is BrainFuse Online Tutoring. And I give a bonus for by utilizing the tutoring center before the week first assignment is due, which is Thursday. Sending me an email briefly describing your experience. You'll earn 4 bonus points applicable to the first assignment. Alright, so the first assignment is assignments. If you've had me in previous classes, assignments were 100 points each. Now they're 10 points each. The first assignment, instead of being worth 10 points, can get you 14 points. So it's a very big bonus. So what I'm really doing is really trying to encourage you to check out BrainFuse once, because when you need it, you might be too anxious to want to kind of figure out how it works. But if you do it when you don't need it, and just, have the experience, and just, have them check one problem, say, hey, I'm not sure that I have this one right, or something like this. That will get you 4 points. And it'll make it so that when you need it, you're comfortable doing it.
I have a question. I use Trio and Jim in the tutoring in Trio Tutoring Center. And I've used him since throughout my college career. He's really been a lot of help to me. Why would I get extra points for using him too, or how would that work?
Send me an email describing that, and I'll give you 4 points for that too. Whatever you use, equivalent to a tutor.
Okay, thank you.
You're welcome. All right, so expectations of me in the class. You can briefly read through those. The graphing calculator. You can use it on homework, but not on tests. You can use a non-graphing calculator on tests. We're going to learn some things about how to graph difficult functions without a graphing calculator. And so the honor system will be very important. They'll be graphing these things and using calculus to get the subtleties of the graph all correct. And graphing calculators are not allowed on exams. And then there's general information about the course. And are there any questions on the structure of the course? All right. If no questions there, let's go to other questions on homework.
Guess we should do
Can
it
you
in
run down
order.
23?
All right. So 23. Gotcha. All right, let's start with 23. All right, now I'm gonna vary my system here, because now one of the disadvantages here is I'm gonna use my camera on a whiteboard here, and so this won't get into the OneNotes, but I'll be able to just do these a lot quicker. So get the camera. I got some cord out of the way. Oops. And y'all can give me feedback on, which system you prefer. Let's try this. So the first one I believe was 23, is that correct?
Yes.
All right. The domain is x cannot equal 2. You just have to make sure that the dividing by 0 is the only illegal operation possible here. That can't happen. And then the range would be all possible outputs from this. Now, all possible outputs, you can kind of tell that most everything is going to be possible here. So I would just say all real numbers. A shortcut for this would be this. Now, once in a while the range isn't all real numbers. We usually don't get fussy about that. And very often on something like this, we really only are interested in what is the domain. Making sure that you don't plug in some illegal value as an input. And the illegal values as input often very important behavior happens right near that. This turns out
I
to be
got a
vertical
different
asymptote.
answer.
Yeah, the book gives us y does not equal -1.
Yes.
Yes.
Now, this
Now,
one
this
as well
one
does
as well
this.
does this.
All right, somebody's microphone is giving us feedback. Okay. Let me look here. This would factor. Sometimes we need to look to see if this factors. X minus 3x minus 2 over x minus 2. This function, normally speaking, this is a vertical asymptote. But in this particular case, because of this cancellation, now this is still, the domain is x cannot be 2. That's still the case, because we'd still get, now we would wind up getting 0 over 0, but 0 divided by 0 is an illegal fraction as well. 0 divided by 0, some people have a hard time understanding, well, shouldn't that just be 0? Because anything 0 divided by anything should be 0. But actually, anything divided by itself should be 1. So it has two different tendencies. On one hand, it wants to be 0, because 0 divided by anything is 0. On another hand, anything divided by itself should be 1. This thing is a contradiction. It's an illegal fraction, so the domain is still x is not equal to 2. This function, though, is really this. F of x equals x minus 3 is the same as this, with the one exception: when x is equal to 2, this one doesn't exist. In other words, if I graph this, this has a y-intercept of -3, but when x is equal to 2, and it has a slope of 1, when x is equal to 2, it doesn't exist. It looks something like this. It has an open circle right over there. Now, the illegal height here is x is not equal to -1. I'm not going to ever ask you for the range and you find out what is the output that is not, you're never going to find on something like this. It's not a very practical question. We usually aren't very interested in that. It can happen, though, that you'll see, of all the different heights, there's one height that you'll never get, which is when y is -1. But it's kind of a curiosity more than an interesting thing that we need to be able to do.
I don't really get how you still got the range for x cannot equal -1. Do you just have
it's
to
not
graph it to
x.
figure it
Thank
out?
you. It's y.
Why, I mean.
Y is not equal to negative 1. All right. When we ask, what is the domain? Remember, like, if we had a function that was doing something like this, the domain would be like all the possible inputs. The domain would be x between 1 and 5. So you really ask, how far left to how far right does this graph go? Okay, and the range is you go from how low to how high does this graph go. Maybe it goes from 1 to 3 or something like this. All right. Now on this one, if we say how low to how high does the graph go, it can go from infinitely low up to a height of -1. But at -1, you don't have a value. You can never have an input that gives you an output of -1. So you'll never get this as an output or a height. And then
So,
from -1 on up, you can go as well. Yes?
so then would you just plug in 2 as the value of x to figure out
Oh, how would
what
you
y
figure out that the
cannot?
y can't be -1?
Right, without
Um,
graphing it.
Really, you'd graph it.
Okay.
And again, it's not a skill that you need to have in the future. I won't be asking you that kind of thing, like on a test. Usually we're more interested in the domain.
But the book thinks we should know it.
Yeah, I think it winds up throwing some strange problems in there just to challenge you at times, even though they're not super essential.
Maybe it's just warming us up for asymptotes.
Maybe. All right, what was the next one that was asked?
Number 9.
Number 9. All right, let me work out number 9 while we take a break. Because we are going for about an hour, taking a break. So we'll take a 15-minute break now. We'll start again at 12:48 p.m. Start again. And when you come back, I'll have number 9 written out on this. And I'll take a little time to explain number 9. But 15-minute break right now. All right, we're back at it again. And on problem number 9, we can see on this picture here the cylinder with a radius of 10 meters, height of 50 meters, and it's filled to a height of h. The volume of water. All right, so first of all, we need these formulas. Area of a circle is pi r squared. And, you know, I've been teaching now for how many years altogether? 30 years I've been teaching math. And one thing I eventually learned was review some of the basics whenever you get the chance. Because just because students are in calculus doesn't necessarily mean all the basics are there. So a couple basics I want to go over is formulas for a circle. Area is pi r squared. Circumference is 2 pi r. All right. These two formulas. Notice on the right-hand side, they use the same 3 symbols. There's a 2, a pi, and an r. And the one with the, if you were measuring in meters, you'd expect the area to be in square meters. So it's got meters squared as its units. And the circumference is just distance around, so it's just in meters. So it makes sense the one with r squared would have to be the area over here. Now the circumference formula, 2r is the same as diameter. It's the same as the diameter times pi. This is the same as saying that pi is equal to the circumference divided by the diameter of any circle. And this has been known for thousands of years, that any size circle, the distance around the circle divided by the distance across the circle is a little bit larger than 3. And that's been known for ages and ages. And this one, pi r squared, if you take a quick picture of a circle, if you have radius r, then r squared is the area of this square right here. So there's r squared. Now, if you take 4 of those r squareds, you'll get too much area. But you take a little bit smaller than 4 of them, 3.14 of those r squareds, and you'll get the area of the entire circle. All right. So some basics reviewed. Now the area of the base with the area formula is pi r squared, which is 100 pi. But not only is this the area of the base, but it's also the volume of the very first layer. If this was 1, the height from here to here, then if you had a thin sheet of this, so the height of the water was just 1 meter, and then you get that kind of that disk, it would also be the volume of that layer right there. And then the volume of the total thing is the same as the area of the base, which is the volume of that first one. Times the height. Because that would tell, the height would tell you how many of those layers there are. And so that's where this formula comes from. It's the same as this, but multiplied by an h. So then it asks you to also find the domain and the range. The h's can go from 0 to 50. And then the g of h then would go from 0 to when you substitute 50 for your h over here. Okay, are there any questions on number 9? Or is that clear?
It asks for independent and dependent variables.
Okay, so the input is always the independent variable. And then the dependent variable is always this one. So the independent variable is the h, and then the dependent variable is what the range is about, and that's always the output, or the g of h. Thanks for clarifying that. Then 57, it says, here's the big function when you composite these two. It tells you what the inner function, now when you have it written as f little circle g, that means f composition g of x. When you redo that, this says f of g of x. You keep them in the same order. This means the same as that. They tell us that the g of x is x squared plus 3. So now we're trying to find the function f. F is something that we do to x squared plus 3 so that its result becomes this. Now, my one possible guess is maybe f of x is, what would I do to this thing to get to this? I got to turn a square into a whole power.
You have to square it.
All right, let's try to square again. If that's the case, then f of x squared plus 3 would be x squared plus 3 squared, x squared plus 3 times x squared plus 3. When you FOIL this out, you get x to the 4th plus 3x squared plus another 3x squared plus 9. Well, that turned out to be exactly what we wanted up there. All right. So what we found out was that's the outer function, just squaring it. And if this had had something like, instead of this, it had plus 15, then we could have something like this over here. As long as this squared gives you this, then tacking something else on could also work over here. Does that clarify for 57, or any additional questions there?
So for that, do you just have to like trial and error it until you get it right?
You gotta think hard and say, oh my God, what can I do to this to get to this? My initial kind of desire was to try to multiply by another x squared. But how do you multiply by another x squared? You can't really do that on a function. But you can, multiply by 2x, but in not multiplying by x squared, but just square the whole input, would take second powers into fourth powers. And yeah, it's kind of a trial and error, kind of, but with experience, you start to see some of these things. Okay. We ready to go on to 33? All right, then 33 as g of x is x cubed, and this one is just asking what is g of 1 over z. And
So do you just cube what g of 1 of z is? So
that's
you would just
right.
cube 1 over z.
1 over z cubed, which is going to be 1 over z cubed. And that's it. And what you get as your final answer then is thus g of 1 over z is 1 over z cubed. Well, by the way, anybody who's done a lot of math writes their z's with a line through them. Otherwise, they magically turn into 2's, and it gets very confusing. So all this is saying is that g is the function that if the input is 1 over z, the output will be 1 over z cubed. That's all it's saying. All right. Does that answer all those questions? Any additional?
So
Go ahead.
is that the same thing as number 34 when you have 1 over x minus 3 and it says f of y to the fourth?
Yes. You're going to substitute that y to the fourth in for the x, and that's all that's going to happen.
And the x is 1 over x minus 3.
That's right. So on number 34, f of y to the fourth is just going to turn out to be 1 over y to the fourth minus 3. Does that make sense?
Oh, you don't raise the whole thing to the fourth power, you just replace whatever x is to y to the fourth?
Yes. What this really means is f of anything is 1 over that thing minus 3. So what we're going to do is we're going to put in the y to the fourth here and here. Any other questions?
Could you do 31A, please?
31a. You know what? I'm looking at that, and that's a long one. And for time's sake, we're going to have to put that one off. Because I don't want to not have enough time for today's.
I feel pretty comfortable. Mike, you want me to post it up on the board?
So what are you saying?
I said, I think I did it right. I feel pretty comfortable with my 31. Do you want me to post it up on the on the discussion board?
Oh, that'd be great.
Okay, I'll do that.
Thank you. And also, I noticed Jay had given some feedback about not having done much with piecewise functions. So I have a worksheet, and I can email you out a worksheet about piecewise functions that I use when I teach college algebra, and I can email you the instructor version of that. And is there anybody else who would like to get a copy of that as well? If you would like that, just send me an email, and I'll get you that. And let's go now to 1.2, representing functions. And I think in here, okay, yeah, we'll do that a little later. I'm gonna do this portion on the whiteboard. So one point two representing functions. And part 1 is translations. Of functions. All right, and we're going to have 3 functions that I start as a basis with. Function number 1, f of x is equal to x squared. Function 2, f of x is the absolute value of x. Function 3, f of x is equal to the square root of x. And with each one of these, the basic shape of the curve, notice that all 3 of these have something in common. You can never get a negative output. If you start with -3 as your input, you're going to get a +9. You're going to get a +3. Oh, you can't even do -3 in this one. It's illegal. But you never get a negative output in all 3 of these. And the basic shapes of these graphs, we're familiar with these. This one is a classic parabola. This one is very much, has a lot in common with this parabola, but it doesn't rise as fast. When the input is 1, the output is 1. When the input is 2, the output is 2. It rises as a straight line. But over on the left, both things never go below the x-axis. And this one, see, this one's not rising as fast as this one rises. And this one is rising even slower. So,
Professor?
yes.
It's sort of, I got the idea that they just exist on the above the x axis, right?
That's
but
right.
we also have to remember that their mirror image, the negative of the function, is the mirror image on the other side of the axis.
Very good. On both of them, they have that same symmetry.
Yeah.
The y-axis is the line that divides it into 2 equal portions.
Right.
Very good. All right, and on this one over here, we can't even put in negative inputs. But when you go out to 9, you only go up to a height of 3. So this would look something like this. Now it turns out, I'm making this one look more extreme, but this is the lower half of a sideways parabola. The lower half is missing. It's the upper half of a sideways parabola. And so it's the same. In this one I made it look much wider than I made this one look. But it's just my scale is very different. Now, on this one itself, if you replaced f of x with y, notice, suppose you tried to get the x all by itself, isolated. See, this is a sideways parabola. And if you had started with something like this, and you had square rooted both sides, remember when you square root both sides, you're supposed to insert a plus or minus sign. And then this would give you y equals plus or minus the square root of x. And you see, this was just the plus part was chosen and not the minus part. The minus part could have been chosen and it would have given you the lower half of that sideways parabola. All right. Now, these are the three basic shapes, and we're going to wind up doing a few things with them. I'm going to erase this over here. In each of these functions, A, create a new function g of x, which is the same as f of x, but part A, it's a vertical shift of 2 units. So that's what I want you to do. And I'm going to give you a quick minute to do this. Write the new function g of x, which is the same as this one, g of x, which is the same as this one, g of x, same as this one, but each one of these has been vertically shifted 2 units. And let me give you a quick minute for that. All right, your quick minute is up. All we do is we stick on a +2. Now, why in the world does this shift everything up? We can see this if we take a little table. X squared plus 2. If I took 0, -1, -2, 1, 2. If I square each of these, and then if I add 2, it takes every single one of these heights and just adds 2 to it. Now, let's look at these as points, one at a time. 0, 0 is this point right here. When I add 2 to it, I'm taking the height of 0 and changing it to a height of 2. So I'm moving it up 2 units. When I take 1, 1, 1 over, 1 up, and when I add 2 units to it, I take the height of 1 and I add 2 to it, and I move it up to here. Every single height is being shifted up 2 units. And so the new graph comes like this. And the same thing is happening with each one of these. We're shifting everything up 2 units. We're shifting everything up 2 units. We're getting these pictures. All right, now, y'all gave me feedback on the practice quiz that you're pretty good with some of these basics. We need to go a bit more in depth here. Let's go part B with horizontal shift. Every horizontal shift comes about from replacing the x with something else. Horizontal shift, we're going to go right 3 units. So, very quickly, write your 1 2, and 3, what your new g of x is going to be in each case.
Professor Shankin?
Yes.
Yeah, I've always thought that this particular thing is really the basis of graphics animation in many of these software packages, because you're starting from one point, you're just adding, like going on a range. In this case, 2 up, right?
Yes.
And so you keyframing the whole way, so it simulates movement, and it's likewise used for of course on the lateral, on the horizontal, or even for scaling. It's the same principle, but in that case, multiplying by a scalar.
Yes, right. We're going to get to all of those. Very
Okay,
good.
thanks.
All right, so let me give you a quick minute. I know I'm kind of moving fast here. These review sections are kind of tricky in that there's a lot of material to cover in a very quick amount of time, but we're just kind of highlighting some of the big features here. All right, we discussed this in the practice quiz. When you shift horizontal shifts, it goes opposite direction of the sign that you would expect. So we're going to replace the x with, now my first instinct would be replacing the x. Instead of putting an x here, I'm going to shift it right, 3x plus 3, but that's wrong, because horizontal shifts go opposite direction of sign. So it has to be x minus 3 squared. And this one over here, I go here, replace the x with, once again, x minus 3. Once again, I replace the x with x minus 3. These would be the graphs, the equations for when it's shifted right 3 units. Now, this is easiest to explain why it shifts in the wrong direction, because we really want to get a feel for why this happens rather than just memorize it. It's easiest to see this over here on this one. Let's look at this function right up here. The domain of this function is x must be greater than or equal to 0. If you put in -1, you can't take the square root. In all of calculus 1, 2, and 3, we're not going to deal with square roots and negative numbers. We're not going to do imaginary numbers. All right. So over here, if you were to look at this and say, what is the domain of this function right here? Can x be 1 now? No, if x is 1, you're stuck. You're going to be getting -2. The smallest that x can be is 3. So x must be greater than or equal to 3. So we must start our graph not at x equals 0, but at x equals 3 over here. So this shape, this one has been slid over to here, and we're going to wind up like this. All right. Now, you can also see it when you come over here. Notice this one, the smallest height you can ever get. You can never get negative heights. But the same is true about this one. You can never get negative heights here. When you square something, the smallest you can ever get is 0. And if you were going to make a little table here, x minus 3 squared, and if you were trying to get the smallest height of 0, what would have to be the input that would give me the height of 0? It's when x is 3, right over here. So we can see that, again, this is moving us to the right, opposite direction over here, and then we're going to have our parabola with the smallest height being over here. Now, even this explanation doesn't really get to the heart of what's really happening here on the horizontal shifts. What gets to the heart of it, I think, a little bit better, to give you a feel for why it shifts to the right, is, let's go back to this one here, and let's look at 2. Kind of a double table for this. If I wanted to do, if I was really trying to graph this thing with easy to use inputs, I would use 0, and the square root of 0 is 0. I'd use 1, the square root of 1 is 1. I probably wouldn't use 2 or 3. I'd probably jump right to 4, so a nice easy square root. And I'd probably jump to 9, the square root is 3. Now, suppose I wanted to get the same outputs over here. How in the world can I get the same outputs? I'm going to have to say, to get the output of 0, I'm going to have to start 3 bigger. So that when I subtract 3, this will be, so what I'm going to wind up doing to each one of these inputs is I'm going to add 3 to them, so that this subtract 3 will cancel with this adding 3, and I'd be back to these, and then I'd be getting those. And so if I add 3 to each one of these inputs, I would be getting a whole new input set that would give me these same outputs over here. If I did this, that's the way that I would get 0, 1, 2, and 3 coming up here. You wind up having to kind of undo what's here so that your input set acts the same as it had done in the past. So you got to wind up just using a new input set. It changes your input set. And to act like the old input set, you got to add 3 to everything. Doing the opposite, it causes kind of the opposite signs. And any questions at this point? If no questions, I'm going to keep going to part C. Suppose I wanted to have a vertical stretch. By a factor of 2. In other words, it's going to rise twice as fast. So for everything to rise twice as fast, what are the new functions going to have to be? And I'll give you a minute to either catch up with your notes, or if you can, take a guess at the right-hand side of those. So let me pause for a minute. Okay, so when I'm going to vertically stretch, you just put a multiplication factor. And if you were okay with the other two, the shifts, you're probably okay with this one. It just causes all the heights to become twice what they were before. The only height that stays the same in that case is when the height was 0. Because if you double a height of 0, you're still at a height of 0. So if I had the normal parabola here, doubling a 0 height still keeps you at 0 height, but this height gets doubled. This height goes twice as long, it gets doubled. Every height goes twice as high as it was before. And now, how I think of it as a vertical stretch is, for me, the visualization that works is I think of rubber bands. On this black curve, the rubber bands go straight down, the red portion of the line below that curve down to the x-axis. On the x-axis, each rubber band is stapled to the x-axis. And what happens when we do a vertical stretch is we pull this black curve upwards, and then every rubber band becomes twice as long as it was before. But the rubber band that has a length of 0 still has a length of 0. Okay, so that's what happens with each one of these curves. And then D, horizontal compressions. Compression by a factor of 2. If we have a horizontal compression by a factor of 2, it's, instead of moving the graph, the black graph up here, upward, we come from the sides and we push inward. And then the heights are going to still wind up going up, but notice every horizontal distance is going to become half of that horizontal distance. So all the horizontal distances come halfway in, and we're going to get more of the vertical. It's going to pull it up more than a horizontal stretch, than a vertical stretch did. And so how is that going to affect my graph and my equation? G of x, normally I'm putting x squared. But horizontal compressions, you replace the x, in this case with 2x, like this. And so then g of x that's actually the same as 4x squared. So now you can kind of see why it actually vertically is rising more steeply, the blue curve, than the red curve over here. And horizontal compression, remember these are opposite of what we had come to expect with vertical. So compression horizontally is going to be big numbers bigger than 1. While vertical stretching is numbers bigger than 1 that I multiply by. If I multiply by 1, it keeps the shape the same. If I use a number smaller than 1 in the vertical sense, like if I used a 1/2 x squared, that would not be vertical stretching, that's vertical compression. It's pushing it down towards the x-axis. Horizontal, everything is backwards. Numbers bigger than 1 cause us to move in instead of moving outward. So a number 2 g of x. Normally I'm putting absolute value of x, but I replace the x with 2x. And that's going to be a horizontal compression. Now this case is going to be the same. When you double the heights on this one, you get this. But when you take the widths and cut them in half, you'll wind up getting the same thing because of the linearity of here. And that's why this is the same as this function. That 2 can actually come out of that. So the blue curve would just be right on top of the red curve here. Okay, and this one, g of x is square. Normally we'd put x, but now we're replacing x with 2x. That's a horizontal compression. Any questions at this point? All right. Let's go with E. A reflection across the, now we can try it in two different ways, but let's try first of all across the x-axis. What would the new equation be in each case if we reflected the first function across the x-axis? So I'll give you a minute to either catch up with your notes or to make a quick guess as to what we're going to get in each of these cases. Alright, so when I reflect across the x-axis, instead of an upward parabola, I get this downward parabola, and all the heights that were positive now become negative. And the same thing happens over here. All I'm doing is sticking a negative sign, turning every positive height into a negative height. Now, it's E, F. A reflection across the y axis. What is my new equation for each of these? Give you a minute to ponder that, to make a guess. Alright, so when we reflected across the x-axis, that's actually considered a vertical transformation. The heights are changing. When we reflect across the y-axis, this is called a horizontal transformation. we're changing x values as we do this. And on horizontal transformations, it's replacing the x. So we go back to this original function. It's something squared, but we replace the x with negative x. Now, when we do a horizontal transformation of this one, the black curve on the right just becomes this curve on the left, and the black curve on the left becomes the black curve on the right, and the whole graph is unchanged. And that makes total sense here, because this negative sign is just going to disappear because it's getting squared. You get a graph that is unchanged. And over here, this is going to be the absolute value of negative x. And the same thing happens here. The function was already symmetric across the y-axis, so reflecting across the y-axis wasn't going to do anything. The absolute value of negative x is the same as the absolute value of x, so the graph stays unchanged. This one, though, does change. Whereas the domain of this one was all the positive numbers, the domain of this one now is all the negative numbers. X must be less than or equal to 0. And the graph of this one is now going to look identical to that, but just going in the other direction, like this. Questions or comments at this point? All right. There are two groups that have new group members. Group 2 and Group 6. We had a person that was added into each group. One of the jobs of the group leader is to keep track of what's going on in the group chat. And if somebody says they have a question, if you agree with that as a group leader, or if you see two people have that question, then you interrupt me and say, you know, what's going on. Also, you are going to get together with your group members outside of class between today and tomorrow at 11:30 and check the homework problems. Today are going to be, the homework is 1.2, and the two problems that I want you to check are 50 and 56. Okay. So in the remaining portion of the time in the class, I want you to set up how you're going to get together to work out 50 and, you know, to look at your answers for 50 and 56. Now, on problems similar to number 50, let me think of it real quick. 50, I think it's, yeah, problems similar to number 50. They're called accumulated area functions. And accumulated area functions are something very different, and it takes a little while to get used to them. Let's start with something that's really, really simple. Suppose I had a function that had a height of 4. And so my function looks like this. And now, although this is f x, let's do it, instead of x over here, I'm going to call it t. T and y. And this function is f of t is equal to 4. Now, my x is going to move somewhere along here. The x might be here. The accumulated area function a of x is how much area I have accumulated as I've moved from 0 up to x. So accumulated area function here would be the area of this shaded region in that rectangle there. And what's happening is x can change. A little later on, x is over here. And wherever x is, we're accumulating more and more area. You can think of the usefulness of this as kind of like, suppose this was the height of a fence. And a of x might represent, how much paint you're going to need if you move out to x units along the x-axis. Oh, I'm going to need to paint, this much area if I go. So the area function is going to get bigger and bigger and bigger. And so we can find out a at certain values. Like if I found out, what is a of 3? Well, then I'd say, all right, now my x is 3. And it's going to be a rectangle that's 3 times 4, which is 12. And I could find out, what's my a of 5? Well, that's, when you're over here, 5 times 4, area of 20. What's my a of x in general? That's when you say, all right, this is x units. Well, this height would be 4. X would be actually the distance from here to here. It's x times 4, which is just 4x. You're going to be doing accumulated area functions kind of like this, but they're going to get more complex. All right, so we're going to stop here. Check in with your groups about when you are going to be able to get together, and if there's conflicts and you need to just break up, like, just us two will get together one time and you other two get together another time, that's fine as well. And I will see you tomorrow, 11:30. Any questions or comments before we
No questions.
Yes.
No questions. I'm good.
No questions, you're good? All right.
Yeah.
All right. We'll see you all tomorrow then.
See you tomorrow. Thank you.
You're very welcome.
Thank you.
Thank you. Have a good one. Bye-bye.
All right, you too. Bye-bye.
Professor,
Yes.
turns out I have a book edition 8, and it's like from 2012. So with reason I don't have the